Good Tuesday to you, everybody in Com 702. Welcome to week boom 7. Hey, we are almost halfway through the semester, which means modular week is coming up in just a couple. So, hang in there, baby, as that 1970s poster used to say, and stay sufficiently caffeinated. Do like I do. Tea, actually, a little late for coffee. Okay, everybody, how are you doing? Are you doing well? All right. Dr. Brown is out of the country, so we are flying solo together. I really don't have a lot of announcements for you, except, labs 6 and 7. Are finished with 6, but lab 7, which you should be working on right now, is over in the assignment folder. I apologize. I don't remember who, but someone emailed me pointing out that there was a duplicate in the answers for number 6, lab 6. I know that. We're sorry. Excuse me. A little bit of allergies as the spring progresses where I live. We will get in and make sure that those are graded appropriately. Okay. It was just a typo. So not to worry. All right. Okay. Let's take a look at the questions for week 6, because this is, week 7. We'll review the stuff from last week. See what you said and see what we can add. We're spending a lot of time looking at regression and regression analysis, and there's a reason for that. It's not the thing in quantitative research, but it makes up the core, right? Because various regression analyses are the best way to determine causality, which is what we're after. This happens, and then this happens. All right. And remember the old adage, as we're going to see here in question number 1, that correlation, just because two things happen at the same time or even in proximity to each other, does not equal causality. All right, let's take a look at question number 1. What are the basic assumptions of the multiple regression analysis, and how do these assumptions limit the type of research that can be used with this methodology? Okay, let's see. Timothy, what do you have to say? A great deal of care should be taken in selecting predictors for a model because the estimates of regression coefficients depend upon the variables in the model. This is from Fields. Let's translate that into some English, okay? Remember, over in British speak, predictors are independent variables. This starts way before you put anything into SPSS. And remember, too, SPSS is a great program for crunching your numbers. SPSS is dumb as a bag of hammers when it comes to telling you whether or not the numbers that you're putting in are correct, have been counted right, are in the right slot. Some of you may have experienced in doing, some of the labs when you first started with the t-test, putting the independent variable in the dependent variable spot or the other way around. And alakazam, SPSS gave you a printout, but it was, it was wrong. I mean, wrong in the sense that it didn't ask the question of was there any statistically significant difference between the means of men who watch social media to strengthen their faith. I'm talking about the lab, and women who watch social media to strengthen their faith. SPSS doesn't know, right? And it's not going to tell you. So even before you start putting your numbers into this program, make sure when you're thinking through your research, make sure that the independent variable or predictor variable, if you like the British speak, actually drives the dependent variable. Because, here's an example. You could take a survey of how many ice cream cones are sold in a city between the months of June and the end of August. And then you could also survey the number of, we hope not, drowning or near drowning incidents in city pools and go, aha, as ice cream sales go up, drowning and near drowning incidents go up. Therefore, you conclude by running your multiple regression model or single regression model, that eating ice cream causes drowning. Well, okay, maybe you have it, you actually have the variables in the wrong spot. Maybe the independent variable is the temperature on the day between June 1 and August 31st. And maybe as the temperature goes up, the amount of ice cream sales go up. And maybe as the temperature goes up, the number of people who go to city pools go up. And drowning and near drowning has nothing to do with ice cream. Do you see what, do you understand? Be careful about what you put in the slot of predictor variable and dependent variable for that matter. But let's get back to you, Timothy. Okay. A model with multiple predictors, 2 or more, constitutes an example of multiple regression. You know this by now, right? A single variable constitutes a simple regression. This you should also know. A single variable represents simple regression. Multiple variables represent multiple regression. Okay, nice restatement. Assumptions based on predictors should make sense, like ice cream and drowning. From a theoretical standpoint, do our predictors make sense? Do they have some kind of measurable correlation to the data? Okay, and not just correlation, causation. Causation. And this is where it's got nothing to do with this model or that model or SPSS. This is where your noggin comes into play. An example used in the text gives the example of record sales, measuring sales compared to how much each record costs to manufacture just adds noise to the variable and the data set. Okay, true, especially if, if the rise in costs is then passed on in the rise in price, then you may have a relation. If the rise in cost is not passed on in the rise in price, then you probably do not have a causal relation, okay? Choosing the bits of data which correlate theoretically allows data to follow more cohesively. Getting an understanding of record sales in this sense should be asking questions about factors directly related to the interaction with each other rather than different parts of the process, which may relate to the topic in some way, but not necessarily the data. Okay, excellent answer. Okay. Question number 2, how do you check your data for normality, homogeneity of variance to satisfy the assumption of regression, and what is data transformation, which is a term I love, and why should you use it? Akoshio, let's take you because this is a really good answer. You're citing Glenn states that the assumption of normality is that the residuals are normally distributed. You wrote it right. I just messed it up. And that your data fits a bell curve shape. Aha, right there. Okay. In SPSS, one of the first things that you can do when you put your data in is you can graph it and have SPSS spit your data out as a bell curve and also select histogram. Histogram, it'll look like a bar graph, okay? But if you trace a line over the top of the bars, just sort of with your eyes, something that approximates a bell curve. Now it could be bent a little to the left or to the right. That's not tragic. That's not inoperable. But the closer to a bell curve, the better. If you have something that spikes really hard on the left, I know you're looking at this backwards, but you get what I mean. Really close to the y-axis and then drops off to the x-axis, you've got a problem in your data. Likewise, if you have something that has sort of this gradual line, along the x-axis, and then suddenly it shoots up as you get over to the right side, shoots up the y-axis, and then drops down, you have a problem, okay? Your data is not distributing normally. This is not homogeneity in your data. Why do you care, okay? Because remember what we're trying to do when we're looking at regression. Okay, this is conceptually really important. What we're interested in is the means of, and we'll use simple regression here. We're interested in the means, the top of the curve of this event, the independent variable, whatever that is, and this event. So the means of, say, the temperature between the date of June 1st and August 31st. So we're looking at the temperature in a whole summer. And the means of the ice cream cones that were sold. Right? If we get, for instance, a nice bell curve on our temperature, and then when we enter our ice cream data, and it's all funky. It's like this. It's like, here's the I got to turn around the other way, but flip around backwards for you. So here's the y-axis like this, and it's like this, and then it slopes up along the x-axis. Something's not right. We didn't collect enough ice cream data sales. We got incomplete sales. There was a citywide ice cream ban, and it shut down all ice cream sales after, July 4th or whatever. Something is going on that is affecting our data. And you're not going to get a comparison of means between the two data sets. Okay, let's go back to you, Akasha. The assumption of homogeneity variance is an assumption of the independent sample t-test and ANOVA, stating that all comparison groups have the same variance. If group sizes are vastly unequal and homogeneity of variance is violated, then the F statistics will be biased when larger sample variances are associated with small groups. Okay. So in other words, back to our example of ice cream cones and temperature. So if we have taken temperatures for every day, but we only took ice cream sales for 15 days, that's an unequal comparison. And we're going to have means that look different, okay? When this occurs, significant levels will be underestimated, which can cause null hypothesis to be falsely rejected. On the other hand, the F statistic will be biased in the opposite direction if large variations are associated with large groups. Okay, there are several options to check for normality and homogeneity, such as a QQ plot graph. Okay, and this is a scatter plot graph where you have like the line that go sort of where the X and Y axis meet. You're looking for a sort of a box shape of the distribution of data points. Okay, a plot graph compares two different distributions. A box plot graph, which will test the distribution. If your data comes from a normal distribution, the box will be symmetrical with the means and the median in the center. Okay, so you're going to have sort of like when we say box, it's really more proper. I'm reaching for a piece of paper here. It'll be rectangular. Okay, so not box and sort of square. So you have and it's going to look like that, right? And then all the little dots, the data points, should fit in that box. Well, now there's one or two, but if you've got a lot, okay, so here's the y-axis, here's the x-axis, and here it is. If you have a lot that's clustered here, right, you got a problem. Okay. So if your data comes from normal distribution, the box will be symmetrical with the means and median in the center. If the data meets the normality assumptions, there should be few cases that differ from the main data trend. To test for homogeneity of variance, researchers use a Levene test. Levene test uses an F test to test the null hypothesis and the variance across the groups. Have we covered the Levene test for normality, for homogeneity? I think we have. Okay, so this is one you need to know. Data transformation, the other part of the question. I love this term. Data transformation is a process of changing the format, structure, or values of the data. To translate that into English, maybe you just throw a few values out of your data set. Now, if you do that, all right, and what do I mean by throw some values out? So, I remember I gave you an example about, let's say you wanted to see how many times a 5-year-old could jump up and down in 30 seconds. Remember that example? And you said you got it in front of the class and you got 10 kids lined up and you said, okay, kiddies, we're going to have some fun. I'm going to push the button on the stopwatch. Say, ready, set, go. And when I say go, you jump up and down as many times as you can. Ready, set, go. And, hoppity, hoppity, hop. First student just hops his little heart out. Second one, third, all of them. And then you get to the fifth student. And that's Jimmy. Jimmy's always a problem child. And he thinks this whole thing is stupid. He's like, he's not jumping. Okay, now, fortunately for you, and unfortunately for Jimmy, no one in the class really likes Jimmy. And, he's kind of a disruption. Okay? I mean, he may go on to be, a problem or a U.S. senator one day. It's hard to tell. Sorry. Okay, and he refuses to jump at all. So now you have numbers for students 1 through 9, and that 10th data point, Jimmy, is a fat 0. Jimmy has got to go out of the data. You just exclude it, all right? But if you do that, if you make any changes to your data set, you've got to tell the reader when you write up your report, hey, we ran a Levine's test for homogeneity, and we had some outliers, is one of the statistical terms, and we removed them. Okay. Now, can that alter the veracity and the external validity of your test? Well, it depends on how much of your data gets the heave-ho. So yes, it can. So, part of the lesson here is to set up survey instruments, survey questions that are clear to the reader, all right, and ask the kinds of questions that you need to have answered to run the tests you want to test. And for those of you who've talked to me, you've heard me say this 100 times. And so for those of you who've never had a chance to talk with me on the phone, I'm going to say it now. When you begin a research project, it is in your utmost interest. So I say, please begin with a solid hypothesis. And if you intend to check the causal relationship between one thing and another, and you're going to need a regression analysis. So, you're saying the increase of this will cause an increase of that. That's your hypothesis, okay? Whatever it is. Make sure that you design questions that report data about the increase of the independent variable and the increase or decrease, whatever your prediction is, of the dependent variable. Use a Likert scale. Use a ranking system. Do not say, well, just tell me about your experience here. Don't ask questions that essentially give you a big pile of qualitative data if you want to run a quantitative test, because, all right. And then secondly, make sure, back to what I first said, this is, once you get a solid hypothesis, make sure that your questions are as clear and straightforward as possible. Fancy language, complicated wording, gone. When you write a question in your survey, a great rule of thumb is do not ask about 2 things in one question. So don't ask, for instance, how often do you use social media and do you like it? No. Now, if you want to find out, and you cross-check by gender or whatever it is after you're finished with your survey, if you want to find out if men like social media more than women like social media, or they like it less and women like it more, or whatever, split those questions into 2 separate questions. How often do you use social media? Do you like social media? Say, respond to the following statement, use a Likert scale. I like social media. Strongly disagree, no opinion, agree, strongly agree. Break them apart. And these are called double-barreled questions. That is, they're asking more than one thing. They ask 2 things. Don't do that to yourself, because it will muddle and muddy your results by confusing your survey takers. All right. And that ups the chance that you're going to get data that's all catawonky and you're not going to be able to use it in the first place. So data transformation actually starts with data collection. All right, sorry to belabor the point, but you can save yourself a whole bunch of headache if you, first start any project with a carefully thought out hypothesis or hypotheses, build your research instrument out from that. And then in doing that, carefully structure your questions so they're clear, they're concise, and they only ask about one thing per question. This will ensure that the data you get is straightforward, simple, not muddy, not because look, if you throw out a survey to say, 5,000 people put their hands on it, which would be great for you, and there's questions in there they don't understand, and they're like, I don't know, and they just start coloring in whatever dot They're like, well, I don't guess. And so you get this question with answers. If you could, because you can run and look at a normal distribution from one question. So let's say it's on a Likert scale, 1, 2, 3, 4, 5. All right. So you can get a bell curve on that. But let's say it's a question that was badly written, and then so you get like answers that are all over the place, and you don't get a bell curve. You get something that looks like a radio wave. It goes, What are you going to do with that? Don't do it to yourself. Okay. Anyway, sorry to belabor the point. Let's go to question number 3. What does Andy Field say is a good way to determine an adequate sample size for doing regression analysis? Find a helpful article on sample size. Okay, Tim, I know we did you before, but I think you hit this one first, so we'll hit you again. Field shares that there is a commonality in the field to automatically assume that a good standard data set will have 10 or 15 cases of data per predictor. That is per independent variable. And I know that's what Field says. Okay, and then you give us a really, really great article to the University of Florida that puts together a document regarding sample size, along with key terms and questions when it comes to utilizing sample size. Okay, I get that. Let me suggest to all of you that you raise the bar a little bit. Elaine, Field explains that widely accepted sample size is a sample of 30. However, samples of 100 yield a better approximation of normal, that is normal distribution. Right there. Make your bottom line 30. Now, I was reading in, this thing leaves a new chair. I was reading in some of your comments and your discussions that are like, I hate collecting huge samples because I got all this data. That's good for you. Okay. Again, be good to yourself as a researcher. Use survey instruments. Electronic does this well, like SurveyMonkey, okay, that can be easily and readily translated into spreadsheet form or imported right into SPSS. So in effect, once the labor, the work in for you, okay, and actually in doing quantitative research, most of the work, where most of the work is really at? It's in the bloody literature review. Okay. It's writing, this is why this is important introduction. And then giving a good treatment of who else has done this before and justification for how you collected data and the methodology used to analyze it and how you coded it, all that sort of stuff. That's going to take you a lot more time than this other stuff, especially if you put your survey in electronic form. You can export that right into SPSS. Hey, in terms of crunching the data and running the numbers, it doesn't take you any more time. I mean, and really import a sheet that contains 5 or 500 or 5,000 responses to your survey. It takes no more time for SPSS to run through the numbers, one or the other. And you get a much richer response. Okay. Now, as both Fields points out, and I think Tim, you make this point. It depends on how strong we want the relationship to be between the independent or predictor variable and the dependent variable, the outcome. How much strength do we want to say, yeah, with X amount of certainty, and that also goes into the my mind's going blank here. Anyway, this is the certainty coefficient, where you said it 95 or higher. How much strength do you want to have? Now, again, be careful, because SPSS is stupid. All right. And SPSS, you run 30 or you run 50 or you run 100. And SPSS is not going to go, oh, well, you have 30 or now that's not very strong. No. Okay. When you write it up and you report it, you need to make your readers aware that N equals whatever. And in fact, for your purposes, as you're researching your papers, and you might be looking at research that others have done, look, and a good abstract will have this. start using your nose to use your head to save your heels. Take a look at that N value. If that N value is below 30, I mean, me personally, if I see an N value below 30, there's no way I'm going to cite the results as statistically significant as has anything to do with external validity. Now, if it's an interesting pilot study, I might say, research suggests, stuff like that. Doesn't mean I just take the article and throw it over my shoulder. But be very, very cautious about leaning on the results in writing your literature review or in your introduction from someone that has that low N value. Look for that in an abstract. Okay, question number 4. When would you use factorial ANOVA and GLM, general linear model univariate analysis? Larissa, you smashed this one, so let's take you. Factorial ANOVA and GLM univariate analysis are 2 different statistical techniques used to analyze data. Well, yes, that's true. I'm not making fun of you, but that's kind of why we're here. Field says that factorial ANOVA is used when we use ANOVA to analyze a situation in which there are 2 or more independent variables. Okay, right? That makes sense, right? Factorial ANOVA is used when you want to test the effect of 2 or more categorical independent variables on a continuous dependent variable. Now, like rolling over in your sleep, everybody should know the difference between categorical data and continuous data, right? Okay. For example, to test the effect of different types of diet and different levels of physical activity on weight loss, which is the dependent variable, right? So weight loss, this continuous variable could be like 0 pounds to 100 pounds to 30 pounds, 50 pounds, like all over the place. Diet 1, diet 2, diet 3, physical activity 1 day a week, 2 day a week, 3 day a week, 4 day a week, 5 day a week. Okay, categorical. All right. GLM, univariate analysis, on the other hand, is used when you want to examine the relationship between a continuous dependent variable and a single continuous or categorical independent variable. For example, if you wanted to study the relationship between the hours of sleep, this is the independent variable or predictor variable, and the number of mistakes made at work, dependent variable. Okay, really straightforward. And when you're in SPSS, I mean, these things are clearly marked in the drop-down boxes. So this sort of loops around back full circle, because the process of which one of these to use starts with the hypothesis in which you are determining, what do you want to ask? What kind of causal relationship are you going to try to get at? And remember, you can, except for things like gender, which is really a bivariate, it's male, female, you can ask questions of anything that generate either continuous or categorical data. It just depends on how you ask it. I mean, for instance, you might say, well, wait a minute, what about stuff like age? Okay, isn't that pretty much categorical? How are they going to be continuous? Well, I don't know. Maybe if you ran the question something like, you used a Likert scale and you said, give your response to the following series of questions, or the following statements. Give your response to the following statements. I feel as if I'm in my 40s. Strongly disagree, blah, 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 blah. Okay, so if someone's 30, they're like, no. Okay, but bam, now you have continuous data that pertains to age. I don't know exactly what you would do with that data from that example, but you get my point. Okay, everybody, have a wonderful week. Okay, keep at it. You're doing great. I'm watching your discussion boards. The one thing that I want to make sure that you're doing, because a lot of you will take the text right out of Field and other places and you like copy paste, which is okay, but be sure that you understand what's being said. I'm not saying that you're not. but read it and be able to translate it back into just plain English. We are communication scholars after all. Okay. Because when you get to the end and you get to the final exam, the assumption built into the questions of the exam is if I say GLM univariate, you're like, oh yeah, okay, I know what that means. All right. So I want you to be prepared. Okay. Okay, everybody. Remember that I'm often thinking about you. I'm just as often praying about you. Have a wonderful, wonderful rest of the week, and I'll see you on Blackboard. Right? Bye-bye.